Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all to lecture number 39 on the subject of computer organization and assembly language programming. The title of today's session is Control Instructions, Part 1. Well, this slide shows today's agenda. As usual, the first few slides will be a recap of x86-64 register set, programming toolchain and instruction categories. And today we are going to talk about the instructions that are used to change the flow of execution of a program, either unconditionally using the JMP instruction or conditionally using the JCC instruction, where this CC stands for conditional code. And there are tens of such instructions that you can find in the Intel Software Developer Manual available at this link at the bottom of the slide. My dear students, in high-level languages like C and C++, we have the facility of control structures like if-else, switch statements, for, and while to transfer the flow of control. But in assembly language, we have to implement this using these jump instructions. And this is what we are going to learn today. So this may be a little bit long session. Let's start playing. So first, a quick recap. Well, this slide shows the register set of x86-64 microprocessor that we have discussed in length in lecture 28 of this course. And this slide summarizes the x86-64 programming toolchain and the layout of the assembly program, and we have discussed all this in detail in lecture number 29 and 30 of this course. If any one of you has not gone through those two sessions, 29 and 30, and he or she is not comfortable with this, I strongly recommend that you should watch those two sessions first and then fall back to this. Well, finally, this slide shows the categories of x86 assembly instruction that we intend covering in this course. And today, and of course in the next session as well, we are going to discuss the control transfer instructions, the unconditional and the conditional jumps. Well, the instruction related to procedures will be dealt sometimes later, inshallah. So to start with, let me precisely describe as what do we mean by control flow of execution of a program. Well, dear students, the execution of every program starts from the label _start as shown over here that define the initial program entry point. And after that, all code runs from top to bottom by default, and the direction of a program flow, this arrow, is called the flow of program. Well, the instruction pointer RIP in our case holds the address of the next instruction to be executed. And after each instruction, it is incremented by the instruction size. And if I assume that the instruction size is 1, so it will be incremented by let's suppose x plus 1, then x plus 2, then x plus 3, and so on. Well, x86-64 control instructions are used to alter the flow of execution of a program based on some maybe event or a calculation or a comparison. And these are the three types of instructions that we intend covering in this course: the unconditional jump instruction, JMP, the conditional jump, JCC, and these are the two instructions related to procedure calls, that is call and ret, that is return. Well, the difference between a call and a jump instruction is that in this call instruction, the return address is saved on the stack before jumping onto the destination level. We will talk about this in detail in some future sessions, and today let us talk about these unconditional jump first. So, dear student, an unconditional jump can be performed by the JMP instruction, which is a single operand instruction. The only operand is mostly a label, but can also be a register or an immediate value specifying the address of the instruction where the programmer wants to jump to. Well, in this code snippet over here, you can note this is the unconditional jump instruction, which is transferring the flow of control to a label named underscore end. So after this jump instruction, instead of executing move rax comma 1 instruction, the control will transfer to the instruction following the label end, that is over here, and will execute the instruction move rax comma 60. And this jump instruction do this by changing the contents of the instruction pointer register, that is RIP. Soon we will see a demo of this. So the crux of this is that these five instructions where my cursor is hovering right now, will never get executed. So the program will print the message 1 that says study call, and this message 2 that is play cricket will never be executed. Rather, this unconditional jump will shift the control to this end, which will elegantly terminate the program. Okay, anyway, dear students, changing the control of flow of execution of a program can be categorized into these four types, depending on where the destination address is: short jump, near jump, far jump, and a task switch. Short jump is a jump where the jump range is limited to -128 to +127 from the current value of RIP. If this is the position of the RIP, we can move 127 locations or bytes down or -128 positions up. And it is mandatory that the code segment will not change by this short jump. A near jump is a jump within the current code segment. The only requirement is that the code segment do not change. Far jump is a jump to a location where there is another code segment. You are jumping to a segment which is not inside the current code. So that is a far jump. We will not be practically seeing this in today's session. And finally, we have the task switch, which is a jump to an instruction located in a different task. Okay, so let us now move to a Linux terminal and see a demonstration of an unconditional jump. Fine. I'm Arif, and right now I'm inside the directory of lecture codes 39. Let me show you the code of let's suppose conditional jump 2.nesum. We have seen the code of conditional jump unconditional jump 1.nesum on the slides. Let me run this unconditional jump 2 instead. Okay, dear students, stop this video right now, make a dry run of this program in your mind, and try writing the output on a piece of paper and then move ahead. And meanwhile, let me assemble, link, and run the program. I will really appreciate if you can run this program in your mind and find out the possible output. So let me assemble by nesum -felf64, the file format -g unconditional jump 2.nesum. So this will create the .o file. Let me link it unconditional jump 2.o. So this has created the executable with the name of a.out. Now I'm going to execute a.out. So it is printing play cricket and then study cool. Is this the same output that you wrote on the paper? Okay. Let's now load this program inside the debugger. Let me load it inside the debugger using gdb-q dot forward slash a dot out in text user interface. And by loading it in debugger and executing it step by step, we will inshallah have a crystal clear understanding of how the program flow works. Let me put the focus on the command window, and let me put a break at the label start. Let me show you the registers by setting the layout to reds, and let me run now. Okay, so this is the register window, this is the source window, this is the command window. Right now we are on the first instruction that says jump to play. uh, well dear students, there are three labels over here. One is underscore play, other is underscore study, and there is another one that is underscore end. Once we are at this instruction, this says unconditionally jump to a label named underscore play. So we will move to this instruction now, move rax comma 1, since this is the unconditional jump. Note the contents of IP right now are 401,000, 401,000, that is at underscore start. And once I press SI, the control will shift to this page because this is an unconditional jump. It says do not move to the next instruction in sequence, rather jump to a location, a named location, which is underscore play. So let me press SI, keep a note of the RIP register. So we have moved on to the first instruction of play. And these are of course the 5 instructions which are going to display the message 2 on the screen. So let me play SI again, SI again, SI again, and this syscall will execute, and now you see message 2, that is play cricket, has been displayed on the output. Right now we are again on an instruction that says jump underscore study. So this is again an unconditional jump which will shift the control of flow to the label underscore study. Let me press SI, note the contents of RIP. So we have moved on to the underscore study label, and this is now the instruction which is going to be executed right now, and these 5 instructions together will display the message 1 on the screen, that is study call, I think. So here you go. So we have the output study call, and now this is again an unconditional jump to the end instruction. Let me press SI. So we have moved on to the last 3 instructions which will terminate the program. Let me press C to continue, and here we go. My dear students, the main aim of executing this program step by step inside the debugger was that you need to understand how an unconditional jump instruction work, how it is always evaluated to jumping onto the label given after this instruction, and you can jump to any label after this instruction, and you can jump to any label before this instruction as well. Let me press Q, fall back to slides and move ahead. So we are done with the unconditional jump instruction. Let us now talk about the conditional jump instructions. Well, the mnemonic symbol for x86 conditional jump instructions start with the alphabet J, followed by one or more alphabets describing the condition code. This CC describes the condition code. Well, if the condition code CC is true, the next instruction to be executed is the one at the destination. And if this condition code is false, the instruction following the JCC instruction gets executed. So this is how it works. unlike the unconditional jump. It evaluates this condition, and if this condition is true, the control moves to this destination, and if the condition is false, the control moves to the next instruction. To implement a conditional jump, the CPU looks at one or more status flags, the carry, zero, overflow, parity, and the sign flag, that are set by the last instruction executed by the processor. And the conditional jump instructions are further categorized into two types, not three exactly: unsigned jumps and signed jumps. Unsigned jumps operate on 0 and the carry flag, and the signed jumps operate on 0, sign, and the overflow flag. And most of the assembly instructions use the CMP instruction before using the conditional jump to set or reset these flags. And I think we have gone through with this compare instruction in lecture number 35, I think. However, here is the recap. Well, this CMP or compare instruction is a two operand instruction that subtracts its second operand from the first operand without modifying any of the operand, and it, however, update the six flags: auxiliary, carry, overflow, parity, sign, and zero according to the result. Well, if operand 1 is equal to operand 2, it sets the zero flag and resets the carry flag. If operand 1 is greater than operand 2, it resets the 0 as well as the carry flag. And if operand 1 is less than operand 2, it sets the carry flag and resets the 0 flag. And I have shown this in these three examples as well, that perform a comparison between the contents of AL register and an immediate value. In this case, they are equal: 60, 5D. Over here, of course, the contents of AL is greater than this immediate value, and over here we have 5 over here. So over here, the contents of AL, that is operand 1, is less than operand 2. Please do the math using a paper pencil to understand completely as to how all these flags are set or reset after the execution of this compare instruction. So dear students, in most of the cases, a programmer normally performs a compare instruction and after that carries out a conditional jump based on the status of different flags. Well, this table gives a brief description of different unsigned conditional jump instructions, which you can use when the operands of the compare instructions are unsigned. If these two operands are unsigned, you should use these jump instructions. Note that the unsigned conditional jump instructions make use of the zero flag and the carry flag only, as I have already said. So if you want to compare, if the two operands are equal, use JE, jump if equal, which says jump just in case if OP1 and OP2 are equal, and internally it will check the carry flag for that. Please understand all these instructions before you use them inside your programs. Similarly, this table over here gives a brief description of some of the signed conditional jumps instructions, which you should use when the operands, this OP1 and OP2 of the compare instruction, are signed. Note that the signed conditional jump instructions make use of the zero flag, overflow flag, and the sign flag. Also note that other than comparing the two operands, there are some conditional jumps instructions which just check the status of a flag. For example, this JG instruction says jump if operand 1 is greater than operand 2. It compares for the zero flag is 0 and the sign and overflow flag are equal. There are, however, instructions which just check for the overflow of certain flags, like JO checks for the overflow flag only. If overflow flag is set, the jump will be performed. Similarly, JC is jump if carry flag is set instruction. That is the unsigned jump instruction. Okay, so now let us do some examples to have a crystal clear understanding of these unsigned as well as the signed conditional jumps. Let us consider this code snippet written in some high level language. Suppose the variable or register AX contains a signed number, and the program checks the contents of AX, which if contain a number less than 0, prints a message negative number and exits. Dear students, as I have already said that in assembly language we do not have the if-else control structure. So if we want to implement this logic, we have to use the conditional jump instruction. So here is the sample assembly code that implements this logic. Note that in the data section over here, we have created a variable message containing string negative number with a new line character, of course, at the end. And this is the length of this string. Well, in the code section over here, first, we have placed a signed number -5 inside the 16-bit AX register. And after this, these are the two instructions that decides whether to print the message, that is, execute these 5 lines of code, or jump to the label end over here without executing these lines of code. Well, the compare instruction compare the contents of AX register with 0, and this instruction in red says jump if contents of AX register is greater than equal to 0 to the label _end. And if this is not true, execute these 5 instructions, that is, display the message, and after that keep moving ahead and execute these 3 instructions to gracefully exit the program. I hope this all makes sense to you. Okay, before moving on to the Linux terminal, let's do another example as shown over here. This is a variation of the previous example, where if AX contains a negative number, the program displays the message negative number. Otherwise, it displays a message positive number. So we have now, if the condition is true, do this, and otherwise do this. Okay, so this is the data section containing this time 2 message strings. Message 1 containing the string negative number, message 2 containing the string positive number, and of course their corresponding lengths inside len message 1 and len message 2 constants. And this is the code section. Remember, dear students, this is one way of implementing this if-else structure shown over here. There can be other ways as well. Well, these are the assembly instructions which when executed will display appropriate messages on screen. Message 1 is the negative number message, and message 2 is the positive number message. Okay, so here is our logic. We place a value 5 decimal inside the AX register, perform a compare of the contents of AX register with 0. If the contents of AX is greater than equal to 0, means AX contains a positive number, we jump to label positive, and here is the positive label. Display the message 2, that is positive number, and terminates the program. Well, if the contents of AX is negative, then this conditional jump, that is jump if AX is greater than equal to 0, will evaluate to false. So no jump will take place, rather the control will follow the next instruction in sequence, and it will display this message, message 1, that is negative number. And dear students, over here do note this unconditional jump instruction to transfer the control to the label underscore end. This is required, otherwise the message positive number will also be displayed along with the negative number. Okay, great. So let's now move on to the Linux terminal and see a demonstration of these programs. Okay, let me clear the screen and let me show you the program. Let me show you conditional jump 2.nesum. So this is the code. This is the same code that I have discussed on the slide. Note that the AX register contains 5 in decimal. Let me assemble this program by nesum -f elf 64 -g conditional jump 2.nesum. Let me link it. Conditional jump 2.o. Okay, so let me execute it. Can anybody tell me the output once I press enter? Since this is a positive number, so of course the positive number message should be displayed on the screen, and this is what it is. Uh, Let me change it. Conditional jump 2.nesum, and let me place a negative number over here. Instead of 5, let me place let's suppose -5. Let me assemble it again. Let me link it and let me execute it. So this time we get the message negative number. Great. Dear students, I strongly recommend that you should load this program inside GDB and then execute it step by step. Check the values of different flags and other registers, especially the instruction pointer, to have a crystal clear understanding of how the conditional jumps instructions use the status flags to decide about the changing the control of flow of execution of a program. Meanwhile, let me fall back to the slides. Okay, so let's now consider this high-level code containing an if-else ladder having two conditions and three print statements. And this is one of the way to implement this high-level code in assembly language. The data section defines three messages to be displayed because we have three messages over here. And these are the two instructions that place a decimal number 5 inside the AX register and a -25 decimal in the BX register. Well, then we perform a compare, and this jump instruction will evaluate to false since it is a jump if equal. So the control of execution will not be transferred to label underscore equal, rather will move to the next instruction in sequence, like this. Now the condition of this jump instruction will evaluate to true since it says jump if AX is greater than BX to this label underscore AX bigger, and since AX is bigger than BX, that is 5 is greater than or bigger than -25, so the control will move on to this portion underscore AX bigger, and this will of course print the appropriate message, and finally it will perform an unconditional jump to underscore end to terminate the program or exit the program gracefully. My dear students, do a mental run of this program by keeping different values inside this AX and BX register, and later on confirm your understanding by loading and step by step executing this program inside the GDB. Okay, so let's see another example. Well, this example contains a condition which is further composed of two conditions and joined by a logical AND operator. So this overall condition will evaluate to true if both these conditions are true. That is, if AL is greater than or equal to capital A and AL is less than or equal to capital Z, that means AL contains an uppercase alphabet, only then this line will be printed. And my dear students, since you know that this is a short circuiting AND operator, so if the first condition evaluates to false, the second condition will not be tested, and the control of execution will shift to the instruction after this AND-if statement. Now this is one of the way to implement this high-level code in assembly language. This instruction moves the ASCII of capital alphabet P, that is 80 decimal, inside the AL register. Then we compare it with the ASCII of capital alphabet A, that is 65. And since JB is jump if below, that is since this P is not below A, ASCII of P is greater than A rather, therefore this condition will evaluate to false. Thus the control does not shift to this label underscore end, rather moves to the next instruction in sequence over here. Okay. So now we compare the contents of AL register with capital alphabet Z, that is 90. Now the unsigned jump above or jump if above instruction again evaluates to false, since the ASCII of P is not above ASCII of capital Z, that is 90. Remember, ASCII of P is 80 and ASCII of capital Z is 90. So jump if above to end, so this is false. So it will again move on to the next instruction in sequence. And the next 5 instructions in sequence will of course print the message uppercase alphabet on the screen, and then of course it will exit the program by calling these 3 assembly instructions. Once again, dear students, if you keep a smaller alphabet over here or a character which does not fall between capital A and capital Z, these lines of code will not be executed. And this was what was required in this logic of a high-level language code. Okay, so this is another example that joins 2 conditions using the logical OR operator, and this will evaluate to true if any of these 2 conditions is true. And since this is short circuiting OR, so if the first condition evaluates true, the second condition will not be tested, and the control of execution will shift to the instruction after the AND-if. Rather, this will not be tested. If this is true, then it will print this yes statement. My dear students, this is one of the possible ways of writing the x86 assembly program implementing this logic. There can be other ways as well. You can think of them. But I strongly recommend that you should try writing or transferring different high-level language codes to the corresponding assembly to have a clear-cut understanding of how the assembler or the compiler later on will compile the high-level language to an appropriate assembly code. Moreover, my dear students, these sample programs are available on the course PUCIT repository. Please download, assemble and load them inside the debugger. Execute them step by step to build up your understanding as to how the control of flow of execution of a program changes during its execution. And you should have a very clear understanding of the unconditional and the conditional jump instructions that x86 use. So that is all for today's session, my dear students. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.